Steve Kimble with PENTA Engineering is going to present on lightning protection systems. And some background information on Stephen. Stephen graduated with a Bachelor of Science in Biology and Zoology from the University of Tennessee in 1994. He joined PENTA Engineering in 2000 as a staff scientist and became Environmental Department Manager in 2007. Since 2016, Stephen now manages PENTA's Lightning Protection System Services Division, where he inspects existing systems for damage and helps clients maintain lightning protection systems on their buildings. Stephen also manages new design and lightning protection system retrofits. Stephen has had extensive training in lightning protection systems through Underwriters Laboratories and manufacturers of lightning protection system products. And he has been active with the Institute of Real Estate Management, or IREM, and Building Owner and Management Association, BOMA. Take it away, Steve.
Thanks, Stephanie. It's great to be here today. Can everybody see the front slide of the presentation? Am I still sharing the screen here? So a little bit about PENTA. We're a fully owned subsidiary of Applied Technical Services. And as Stephanie mentioned, I run our lightning protection systems division. And we also do, between both companies, facade access and fall arrest consulting, parking deck evaluations, structural design and remedial services, roof design and consulting, and basically help building owners with problems with their buildings. But today we're here about lightning protection and lightning in general. So just, you know, when you search lightning protection in Colorado, you automatically come up with quite a bit of several instances where people are getting hurt. And what I found out is the Denver area is actually in the top 10 in the country of people getting struck by lightning. There's just tons of news stories, but you know, it hurts people, strikes people 29 more times than tornadoes. And so when thunder roars, you want to go indoors. Nowhere else in Colorado sees as heavy of a density of lightning strikes than the counties that straddle the Palmer Divide and the east to west ridge south of Denver, where Pike Peak is. Now, if we look at U.S. lightning strikes per year, Colorado in general is generally low compared to many other areas of the country. I'm in Atlanta, Georgia, as I mentioned. Florida basically is the capital for lightning strikes in the country. But you have a real hot spot just south of Denver. If we blow that up, we actually see where the majority of the lightning strikes are hitting in the Denver and south of Denver. If we look at lightning fatalities by state, as I mentioned, Colorado is in the top 10. I believe it's number 4, if I recall correctly, and Florida is definitely the highest. One of the reasons for that is a lot of people really enjoy the outdoors and doing a lot of outdoor activities. Well, we estimate about 30% of all electrical outages are lightning related. That comes from the electric power industry. And insurance companies categorize about 5% of all paid claims as stemming from lightning effects. And that was 1999 data. It's pretty tough to come up with a lot of current financial data. Most of what I find is at least 5 to 10 years old, some older. But lightning can do an extreme amount of damage, not only to people, but also to buildings, property. These are a couple buildings in the Atlanta area that have been struck. And the lightning causes an estimated $4 to $5 billion in annual losses from $1999. The current of a strike can approach 400 kiloamps, and about 50% average of strikes are at least 25 kiloamps. The NFPA, National Fire Protection Association, has a standard NFPA 780 that we use in this country for design of lightning protection systems. And also Underwriters Laboratories, UL, has 96A. And the two standards basically mirror each other with very slight differences, but those are our design standards that we follow here. And this, we'll see if this will play. This is a lightning strike of a building here in Atlanta that was captured. And you can see just the raw power of the strike and then the sparks that came off. This facility did have a lightning protection system. ATS actually works on this building and was able to talk with the engineering staff following the strike within a day or two. And they reported that no critical building systems were damaged as part of that strike. Then ATS also is doing a rooftop lightning or rooftop anchor inspection, looking at the safety equipment on a building in Chicago. And this is the Sears Tower. And a thunderstorm came up, so they got inside the building and decided they'd take some video and happened to catch the Sears Tower. And you can just see the enormous amount of energy that goes through these buildings. We do not have contacts in that building, so I'm not really sure what type of damage. But why does lightning form and how does it form? So in general, as a storm cloud builds, there's a charge separation that occurs within the cloud. Negative and positive ions, and negative cloud base induces a positive charge at ground level. So you end up with a lot of positively charged ions at the ground level. Step leaders ionize the air and they start to form a path to the ground. And as soon as that path is connected, then you have an energy exchange between the cloud and the ground. And that continues until those negatively charged ions have reached the ground, and the cloud then is no longer polarly charged. Here's a few other ways to kind of show what's going on with a lightning strike. Basically, you have the negatively charged ions coming from the cloud. The step leaders actually start from the ground and work their way upward. And here's another depiction. This is with a lightning protection system that kind of shows how it helps the leaders start at the lightning protection system to make the connection there. The entire purpose of a lightning protection system is not to prevent a lightning strike, but to provide a preferred pathway of the energy from a strike to the ground. So it goes the route we want it to and not into the building where it affects all the critical building systems. Benjamin Franklin's lightning rod is still the system that we use today. And even in 1752, when he first developed the lightning rod, he was thinking how it could help preserve property, houses, churches, ships, and protect people. And it's still, the Franklin rod is the preferred method of lightning protection. So how do lightning rods work? Basically, when they are installed on top of the building, we want them to extend a certain height above anything that we're protecting. We're going to create a zone of protection with lightning rods. And then they're made of aluminum or copper, and every component of the system is made of aluminum or copper, and it conducts the electricity to the ground using what we call a down conductor, which is just a long cable that's connected to either a ground ring or a ground rod. So again, we're providing that preferred pathway, make sure that energy goes straight to the ground and not into the building.
Hey, Steve.
Yes.
Can you tell us what a step leader is?
So if we back up just a little bit,
Sorry, I just want to.
the step leader is the part of that return stroke. Let's see can you see my mouse in front, or is it only showing? Okay.
On the bottom middle.
So the step leader is the part that starts from the ground and works its way up. I think you get back over to this one may show it a little bit easier. The step leader would be the blue that's going to start coming from the air terminal and working its way up. And from the cloud, this is also the second leader. They're just differently charged. One's positive and one's negative. So as I mentioned, lightning definitely causes a lot of issues to buildings. Some of it's physical damage, a lot of it's electrical damage. But even outside of the physical damage to a building comes the downtime of your tenants. And depending on what type of tenant you have in your building, this can be astronomical in cost. Generally, unplanned downtime costs Fortune 1000 businesses $2.5 billion a year. And it can be an hourly cost for infrastructure failure of as much of $100,000 per hour, or if it's critical systems like the NASDAQ trading or 911 services or anything like that, it can be exponentially higher. We do a lot of work with AT&T and Bell South telecommunications facilities, and they basically, the number one rule is don't do anything that results in a service outage, and those outages can be astronomical in cost per hour. But here is where we have lightning strike that has hit the corner of the building. Here it looks like it hit right at the electrical service entry. Here's another corner of the building. Carnegie Mellon survey. So about 30% of all US businesses will suffer lightning related failure or disruption. And even though we know this, only about 10% of the new buildings are constructed each year with a lightning protection system installed. That seems to be value engineered out many times. I believe more and more people are recognizing that it is necessary. And we're expecting lightning strikes to grow. Changing weather patterns mean lightning strikes are expected to grow by 50% this century. And the costs are increasing an average of 20% a year. So lightning storms can knock out utility and paralyze engine generators in a single strike. So with data centers, 19% of data center sites that experience the lightning strike experience some type of outage or loss. Looking around, a lot of our clients really want to know, well, how much does an actual strike, if it costs, X number of dollars to install a lightning protection system, what are the costs if I don't have one? What kind of damage can it really do? This is an example of a municipality in Ohio, and they did install a lightning protection system, but they had some deficiencies in the way that was grounded, as well as some deficiencies in a radio tower and the grounding plan. And they got struck several times. The first hit just hit a few communication boards, and it was about $4,600 worth of damage. Then they got hit again the following year in 2005. Tower, radios, telephones, surveillance cameras, emergency generator, a few other things were hit. And it took almost $23,000. Then in 2007, they were actually hit twice in 2 weeks, And the total for that ended up being over $100,000 worth of damage. They finally got to the bottom of what was causing it, and it was an issue with the way things were grounded, and they were able to fix that and keep it from happening anymore. Outside of the physical damage to buildings, we also have light fires that are caused by lightning. You know, in the general biological realm, lightning is a normal part of forest management and fires. I know you guys are probably pretty familiar with that. I'm not sure if any fires currently were started by lightning that are going on in your area or California, but estimated $451 million in direct property damage between 2007 and 2011. But of that, out of that 451 million, it's estimated 15 million in business properties such as offices and specialty shops.
Hey, Steve.
Yes.
We've got another question for you.
Sure.
Jake Schley says, do the leaders you mentioned create a desired or more preferred path for lightning to grab over another avenue?
Well, the leaders are where those potential energies are building up. So that's going to become the pathway. And so with the lightning protection system, we're wanting the air terminals to be the areas that are generating those leaders, because they have such a quick flow to equalize all of the different ions between the ground and the cloud. So yes, we're trying to create those pathways. There are some alternative systems we'll show you in a little bit that are called early streamer emissions, and they would claim that they would generate the leader and actually more or less cause lightning to strike that particular air terminal and pull it to ground. Some of them were even charged with radioactive sources. In the end, the United States does not recognize that they provide any better protection, and there's been numerous cases where their claims have been debunked. But the leaders are basically the points of the energy differences, and the lightning protection system is generally the air terminals. By placing them where we're placing them, those are going to be the points where those leaders would generate. I hope, does that answer the question? So the rooftop lightning protection is really one part of a complete protection against lightning. Lightning protection, rated surge protection is the other half of the battle. So we want surge protection. The lightning protection on the rooftop is going to protect the building somewhat from a direct strike, but surge protection protects from adjacent strikes and energy traveling in on various service entries. And that needs to be not only on the electrical service entry, but also any conductive signal path. So your data, cable, communication lines, phone lines. Generally, let me see if I can get my mouse back over here. A type 1 surge protective device, SPD, installed at the main electrical service entry, or you can have a type 2 device that's installed on the load side of the service panel. And that protects anything between coming in on the underground electrical service. That has to be rated, as I mentioned before, 50% average of lightning strikes is 25 kiloamps. So NFPA and UL require that the type 1 and type 2 surge protective devices be rated at 25 KA. Then we also have a type 3 surge protective device that's installed to cover cable, phone, any other communications type service. It can be your video cameras out on the front, like on the front gate or anywhere on the outside. The typical commercial lightning protection system might look something like this. This is laid out in accordance with NFPA and UL. And we have air terminals. There are basically three names: air terminals, strike termination devices, and lightning rods. All generally mean the same thing. And so depending on the height of the air terminal, these are spaced either 20 or 25 feet apart. They're interconnected with a conductor cable that maintains a downward or horizontal path. And depending on how tall and the geometry of several things we'll get into in a little bit, we have air terminals on mechanical equipment on the roof, and everything's interconnected with two paths to ground to the perimeter loop. And the air terminals are within 2 feet of the perimeter edges of the building. And then at least once for every 100 linear feet of building perimeter, there'll be a down conductor, which is a cable that takes this energy all the way to the ground, where it's interconnected with ground rods. And if it's a steel frame building, the rooftop system can be connected just under the roof level to the structural steel. Use the structural steel to carry the energy down to the ground, where we have another connection that takes it out to a ground rod. Or this can be a physical cable that's either run in a concrete column or somewhere along the perimeter edges of the building. And then at the base of the building, we'll go out to a ground rod or a ground ring. This is a down conductor. This is a through-roof assembly that in this case takes it to structural steel. If it is a concrete frame building, it would just go straight to, the cable would go all the way to the ground. So I mentioned the zone of protection. If you imagine a 150-foot radius sphere, a big ball sitting on top of the building with, from one air terminal to another, we roll that ball around on the roof, resting it on top of the air terminals. And if we have a lower section of the roof, like between a penthouse and the parapet wall, anything on that roof that does not breach the curvature of that sphere is called, it falls within a zone of protection, and it doesn't need air terminals or lightning rods on it. Sometimes lower roof edges that jut out may be covered and not need lightning protection, but if you have a lower roof edge that juts out far enough, you do need additional protection on that lower roof level. So general layout considerations: the air terminals need to stick 10 inches above the object they're protecting. They need to be within 2 feet of the building perimeter and roof edges. So if on chimneys, they need to be within 2 feet of the edges, also on mechanical equipment. If an air terminal is more than 24 inches tall, it needs to be supported at least midway up. I'm kind of going through a lot of these things because we see a lot of companies install lightning protection systems, but we see very few maintain them. And when we're on top of roofs looking at other things, we're seeing just a lot of damage to the existing systems. And if the existing system isn't functioning properly, providing that preferred pathway to ground, then it's going to allow lightning energy to go into the building where we don't want it. And so maintaining the system is very important to ensure that it's working properly. There are a couple different classes of components. There's class 1 and class 2, and it's based on the building height. Class 2 starts at 75 feet. Class 1 is for buildings less than 75 feet. Basically, class 2 is a thicker gauge of material because it has to transfer that energy further, so they require it to be a thicker gauge. So there's a difference. As I mentioned, there's copper materials and aluminum materials. Copper is a better conductor, so it doesn't have to be quite as thick to carry the same amount of energy. We'll have either on a class 1 building that's less than 75 feet, that most components are going to be, the air terminals will be 1/2 inch solid aluminum or 3/8 inch solid copper. On a class 2 building, class 2 aluminum would be 5/8 inch thick air terminals or 1/2 inch thick copper. One of the other things we routinely see is a lot of architects will spec a copper system, and copper does last longer than aluminum, but it doesn't play nice with a lot of metals. We get what's called galvanic corrosion when we have contact of copper with dissimilar metals. In this instance, this was actually a tin-plated copper conductor, and it was connected to aluminum air terminals. But everywhere this copper conductor was in contact with the mechanical unit, it started rusting out. And we see this routinely with copper that's attached to metal coping on parapet walls. There are a lot of other things wrong with this picture and the way this was maintained, but the main goal for this was copper on metal coping. We see this many, many times, and it needs to be replaced. This should be aluminum everywhere the conductor is in contact with metal. And then the aluminum can transition back to copper where it runs across the roof and is not in contact with metal. This was a fully copper system that was installed on structural steel, and then the copper was routed into a galvanized steel conduit. This is the down conductor. Copper cable would actually extend all the way to the ground. But this is a really good evidence of galvanic corrosion and what happens with prolonged moisture exposure between dissimilar metals. Here we have an example of a bimetal connection. It's kind of hard to see in this photo, but there's a thin wafer that runs between these two clamp pieces, and one side is copper and the other side is aluminum. So we can mix the metals as long as we're using a part to join them that is designed to prevent that galvanic corrosion from happening. Here's another example of an inline bimetal connection. This is part of a down conductor that was mounted on the exterior of the building that was routed to the ground. And as I mentioned, air terminals need to be within 24 inches of an outer edge. And in this instance, the original air terminal was within 24 inches. It got broken, and the replacement contractor installed one that was more than 24 inches. So when we did our evaluation, we noted that, and we had to basically remove both of these and install one within 24 inches. And if you remember from one of the earlier photos, several of those photos were where lightning has struck the corners of the building. The air terminals have to be spaced no more than 20 feet apart if they're less than 24 inches tall. 24-inch tall air terminals, you can make that space in 25 feet. The conductor has to be securely fastened every 3 feet. So we have a lot of areas where the fasteners have become detached. And then looking at zones of protection, we have air terminals along this wall, but we didn't have any air terminals on the cooling tower handrails or the piping, the condenser water piping serving the cooling tower. So in this instance, that 150-foot radius sphere, if you roll it along the air terminals on the perimeter, it's going to hit the handrails and the piping. So we need air terminals here. This is an example of how a cooling tower should be incorporated with lighting protection. See a lot of instances where the original design of the lighting protection contained air terminals where they were necessary, but then a new tenant comes in, adds new mechanical equipment, and therefore needs to have modifications to the lighting protection. Then once you add lighting protection on this condensing unit, these then would not be needed, because we would have that ball could rest here and roll over onto here and not touch here. But you wouldn't necessarily have to demo those. They just wouldn't be necessary. On buildings where we have a lot of different types of antennas, a lot of times it's not feasible to put an air terminal on top and have it within 24 inches of all the outer edges. So NFPA and UL allow for omnidirectional antennas that we bond to the base of the antenna, and they call this sacrificial antenna at that point. So if lightning strikes, it may damage this antenna, but then it should catch the lightning protection conductor and go the route we want it to at that point. Another area we see a lot of issues with is with tall buildings and balcony levels. If you have a building that's over 125 to 150 feet, that rolling sphere is going to go straight down the side of the building. So anything that juts out needs protection. In this case, this was a 18-story building, more than 150 foot tall. So from this level, the sphere would just roll straight down. So we need lightning protection out here on this outer perimeter of these balconies. It's a lot easier to do during building construction because all those details can be hidden in the columns. To add it at this point, air terminals on each level require 2 paths to ground. So we would either have to install additional down conductors on the interior, which means coring through every floor and routing that cable all the way to the ground, or installing it on the outside of the building as inconspicuous of a place as we can. Many building owners really don't want to see the exterior cabling. So with rooftop units, there are some exceptions in NFPA that allow you to mount metal to metal contact and just have the air terminal mounted directly to the top of the unit with a bonding connection at the base. We prefer to do what we call a halo drop, which basically interconnect the air terminals on top, air terminals within 24 inches of the corners, and then provide it with 2 pathways to ground to the rest of the rooftop system. And this is a unit where, for some reason, these air terminals are side by side and not on each corner. And again, the conductor is not securely fastened every 3 feet. Powered rooftop units with mushroom fans, as long as this fan is less than 4 foot in total diameter, we can have just a single one on top because we're within 2 feet of the edges. But the air terminal needs 2 paths to ground. They allow up to an 8 foot dead end. So if this total length of cable joins with the main roof conductor and it's not more than 8 total feet, this would be allowable. This one was over, so it actually needs a second path. The same with this unit. This was more than an 8 foot dead end, so we needed to continue this path and give it a second direction to go. On this facility, this was way more than 8 foot dead end. So what happens is it just doesn't transfer the energy as quickly as it should. So this might not create the leader that we want it to create, and might not give it a favorable path to ground. So this corner is still not truly protected. And then our Thru-Roof connections, because the preferred method for most building owners is to have the lightning protection to go down through perimeter columns. NFPA and UL want those conductors to be as near as practical to the outside edge of the building. We aren't wanting to bring that energy in through the core of the building and then have to take it back out again. So this can be, just a pitch pan with raw cable going straight through. It's very tough to waterproof a stranded cable. So we have a Thru-Roof assembly, which is a threaded rod going through PVC. So we have a cap and different waterproofing details. This is more of a standard electrical part, not really approved for lightning protection. The conductor, NFPA and UL state that the conductor needs to be routed in a manner that doesn't create more than an 8-inch bend radius, which is about like a 90-degree elbow in a 1-inch PVC conduit. And so the tighter, kind of like with the garden hose, the tighter you bend the hose, the more the water flow will slow until you eventually kink it and cut off the water flow. Same is kind of true with the lightning protection energy going through a conductor. The tighter bend is going to want to try to keep going straight and have a better chance of arcing off into something we don't want it to arc off into. So this was too tight of a bend, even though it does give a decent waterproofing detail. These are much better down conductors and the through roof assemblies. We've seen many times where you have a beautiful rooftop system. In building construction, a lot of times an electrical contractor is hired by the general and they do everything inside the building. They do the grounding at the base of the building. They route all the cabling up through the building. And in this case, just on the underside of the roof, the down conductors were routed by the electrical contractor and they exited just under the roof from this column line. And then it was handed over to the lightning protection contractor, and they did a beautiful job on the rooftop, but they never connected the two. They never connected below the roof line to the down conductor. So again, having your system inspected by a qualified professional is very paramount to ensuring that you're getting what you paid for and that it's actually working and doing its job. So as I mentioned, you can install down conductors on the exterior of the building. In this case, we were actually, these were originally exposed. The building owner didn't like the look of it, so he asked that we paint match the conduit as close as possible to the concrete facade. Others allow just even come down the exterior of the building, it still has to be securely fastened every 3 feet. If you use aluminum as the down conductor, it has to transition to copper within 18 inches of the ground. Aluminum conductor cannot be buried, cannot be in contact with the ground because it deteriorates rapidly with the soil conditions. And if the down conductor is in an area that's subject to physical damage, it has to be protected along the bottom 6 feet. So if the landscaping crew with their weed eater can come by and cut this, or if it's close to a walkway, anything else that may physically damage that conductor cable, we got to protect it from physical damage.
So Steve, out here in Colorado, would snow be a reason for protection like that last picture?
If you're going to be shoveling the snow or something that basically you're trying to protect the strands of the cable from getting nicked and cut to make sure that they all stay intact. So it's more of a physical damage. Snow itself, freeze, melt, thaw, is not going to really damage the cable. It may separate the strands over time, but in general, we're really dealing with more physical activity. So if it's in an area where you may be having to shovel and you might be banging it with a shovel, it should be protected. Now, I mentioned the bend radius issue and U-pockets. So NFPA and UL both state that lightning protection conductor needs to maintain a horizontal or downward path. It does not like going uphill. It can go down as fast as we can take it down, but they do not want the conductor to rise at greater than a 1/4 slope. So 1 inch for every 4 inches horizontally, or 1 foot for every 4 feet horizontally. This is a U-pocket. So we're coming down off of a parapet loop over to a down conductor, but then we're rising at too great of a slope. And then we also have a bad bend here. It's a good waterproofing detail, but it really is not doing a lot. And the energy of a strike is going to try to arc off it around here and try to find a different pathway. In this particular photo, there's not many other pathways near, so it might still function as designed. Same thing on outside and inside corners on parapet walls. The correct detail I've got in the next photo should actually generally bring that conductor up and over these corners. So this was how we repaired kind of a big mushroom bend. It's greater than 90 degrees. We just give it a better pathway to follow. Here's an example of a proper rise. So this portion of the cable is coming from the penthouse, comes across the roof. And in this situation, the down conductors are on the outside of the building. So all of the conductor from the penthouse lightning protection has to come over, and any energy from a strike has to climb this wall to get to the parapet loop and then down to the down conductor. So this was installed at a 1/4 slope. I believe this was about a 4-foot parapet wall. So that rise had to run horizontally for 16 feet to make that height. This is a roof that probably was initially a ballasted roof. And for those that don't know, a ballasted roof is covered with river rock or stone or some type of other gravel aggregate. It was replaced with a rolled roof, but they left all of the standoff blocks, and these are no longer spaced at 3-foot intervals, so our conductor is not securely fastened every 3 feet. This is also a bonding connection to a tie-back safety anchor that a window washer would tie off to. And they attached it in a manner that really limits the use of that anchor and could potentially cause a dangerous situation for anyone using that. If they're tying a rope to that anchor, we have sharp edges that could cut that rope. So we would have a clamp around the bottom. This would be installed, all the conductor would be installed in a neat professional manner, going in more straight lines and securely fastened to the roof using sacrificial pads, basically little small squares of the roofing material that the roofer would install, let us install that. And with TPO or PVC type membranes, we still need the cross-run conductor secured every 3 feet. Depending on the manufacturer of the roof, some manufacturers will let us adhere the cable hold down clips directly to the roof surface. Some require these sacrificial pads. So if you're doing a re-roof and you want to reinstall a lightning protection system or install a new system, be careful when you're getting bids, because a lot of lighting protection contractors just automatically exclude the sacrificial pads, and that can add up to a sizable job by a roofing contractor. Some of these rooftop systems where they have to be adhered every 3 feet can be hundreds of locations, and those sacrificial pads, you know, they could add anywhere between, I've seen pricing between $10,000 and $50,000 for the roofer just to install those sacrificial pads, depending on the size of the roof. Grounded metallic bodies, anything that shows continuity with the building electrical grounding or the lighting protection grounding, we need to install a equipotential bond that creates a pathway to prevent those ion differences from building up, so we don't create an area where it's going to try to create its own leader and jump off and arc into other areas. So generally within 6 feet of the conductor, anything that's a grounded metal body, we need to bond to the lighting protection system. It is a physical connection. Usually it's smaller diameter, smaller gauge than the lighting protection conductor, but it keeps those differences, those energy differences from building up. So here we'd have little small clamps with a smaller wire connection to make sure the energy is not going to jump from our down conductor to the electrical conduit and find a different pathway into the building. This is a cooling tower. They did a bonding connection, but they actually did it below the spring isolation. So this is an isolation connection that prevents vibration of the cooling tower from transferring into the building. But by its very nature, it's isolated, so it's not electrically continuous. So we want to make sure that these connections are up on the body of the cooling tower supports. Our preferred method is actual conductor coming from the top of the cooling tower if there's air terminals on top of it to connect those. We have a lot of communications equipment. More and more cell phone providers are renting rooftop space and putting antenna sleds. The lighting protection should be an independent grounding system. Communications equipment should be using the building's grounding system, the electrical grounding for the building as their grounding. We should have a bonding connection to make sure we don't get potential energy differences between the equipment. But satellite dishes, antenna cell towers, they see this lighting protection conductor, they know it's a great ground, and this prevents them from having to run another 100 feet of cable to get to the building. So many times they just attach it directly to the lighting protection. That this is not approved by UL for lighting protection systems. It's an undersized bond. It's not approved to carry the energy. And it could also backfeed into the actual equipment and make that equipment go down. We mentioned the alternative systems. And so here are some of the ones that we've seen and some that are out there. They're really big in France and Malaysia. And these are some of the early streamer emission air terminal heads. And so their claims are they will create that streamer and basically encourage any lightning strike to be directed at it and down to the ground. And they claim enormous zones of protection. So instead of having an air terminal every 20 feet around the perimeter of the building, their claim is we can put one air terminal on top of your building and it's going to protect your entire building. This is a dissipator array air terminal. And again, by making all these little small points, their, I guess, claim is that lightning will be attracted here versus other larger points. What we've seen happen with this type of air terminal, the one on the far right, is if that gets struck, all of these little small points turn into molten metal that then rains down on your roof.
Hey, Steve, we've got some questions.
Yes.
Let's see. First question. Once you do the initial inspection and verified the system is functional, how often do you recommend inspecting the system afterwards? And ATS, do you provide inspection services with a full report?
Yes, we, NFPA and UL recommend that the, some are a little bit open. They say periodic, it depends on the area. NFPA actually does recommend annual inspections. It also should be inspected anytime any mechanical equipment is added. We see window washers many times damage the lightning protection as they're going over the edge of the buildings if they're using rope access. So the recommendation is an annual inspection. If you have a UL master label, which UL is another third-party firm, they will come out after a system is installed if it is applied for a master label, and they will do a third-party inspection, then issue the master label, and that is good for 5 years before it has to be recertified. We work with UL. We can have UL come out and inspect after us if we install the system, and then the annual inspections will ensure that it stays in accordance with that label, and then we'll have UL come back out at the 5-year mark and reissue the master label. Then we do issue reports. PENTA and ATS do the inspections. They issue the reports. We are a UL listed installer, so we can do all the repairs. We can also design and install new systems. We work with a manufacturer and we can get just about any component that's necessary to do any of this.
Great. And then there's one additional question from Jason. Stephen, do you have any stories or experience with a scenario where the lightning protection system does its job on the roof, but then fails somewhere inside the building before it gets to the ground?
I guess it's kind of hard to say. If it did its job on the roof, it wouldn't really get into the building. But that being said, we do have several clients that have been struck and either received no damage inside the building or and no damage on the top side. And then there's been a few times where I've seen the lightning rods get burnt and just limited replacements, limited components of the actual lightning protection need to be replaced after a strike. It all depends, you know, I mentioned that strike energy can be, you know, 50% of all strikes are 25 kiloamps, where they can be as high as 400 kiloamps. And that's a huge difference in strike energy, just depending on all of those potential energy differences. So no lightning protection system, and even UL in their master label, there's never any guarantee that no damage is going to occur because you have a lightning protection system. It is just simply shown over and over that it greatly enhances or it greatly limits the effects of lightning strikes on the building. So this is another picture of an ESE air terminal, and this is kind of their general thought. And we've seen several, even though NFPA and UL don't recognize these systems, they are being sold in the United States. There's several of these in the Atlanta area that I've seen, some with buildings that were constructed just in the past few years. The NFPA and UL, they're not building code, so there is nothing that prevents them from being installed. U.S. military base will not let the alternative systems be installed. It has to be a Franklin rod type system. And University of Florida, a lot of these were being installed in Florida. And they connected a study nearly 20 years ago and just absolutely debunked the scientific theory of the early streamer emission air terminal. And so here's one, and 30 feet away, the corner of the building got struck. So it did not do its job. That kind of comes to the end of what I've got, but we're definitely available for any kind of questions. I hope this showed you some things. If you do have lightning protection systems on your building, showed you some examples of things that we've seen that have been wrong that need to be addressed. And, you know, as I said, I'm open for any kind of questions.
All right, we got one from Wayne. If you get struck, do you need to conduct a re-inspection?
Yes.
Good.
If you're pretty confident the building was hit, we definitely need to come take a look at things and make sure there weren't damage to components, and make sure everything's still working properly. And for folks, if Stephanie is there in the Denver area, she can definitely help out anyone locally, and we can get out there usually with, you know, on a pretty timely schedule.
Stephen, this is Craig Johnson with CBRE. I'm also the president of BOAC. I wanted to thank you and Stephanie. I know Stephanie's been trying to get this set up for quite a while, and then all of a sudden with COVID hitting, things kept getting pushed back, but see a lot of value in this. A lot of times these lightning protection systems get left unseen and untested and unmaintained in that because they're out of sight, out of mind. I mean, we only see them when on the roof or when somebody damages them. But after your talk and everything, you know, really realize the value of them. And it's like you said, I mean, it's one strike can put you down for quite a while, and the cost that's associated with that, with your tenants in the building, that if you're down for a long period of time can be astronomical. And we don't want that to happen for our clients. And so thanks again, Stephanie, thank you. Just wanted to say that I appreciate everything you guys have done.
We actually have 2 additional questions if we've got just a minute extra here.
Sure.
Jake Schley asked, do you have experience with systems that deflect a strike? He doesn't recall the name of those.
Those would probably fall under those alternative systems. UL is kind of muddying up the waters a little bit. Again, they're a third party. A lot of people, they're so huge. A lot of people think they are the government, but they are a third party firm that does these inspections. And for years past, they would not inspect the alternative systems. They would just say they don't comply with UL 96A or NFPA 780. And I think they've started bowing to financial pressures, and now they will go inspect these alternative systems and give you a piece of paper that might lead someone to believe that it's compliant, but all they're going to state is it's in compliance with the manufacturer's requirements. So they're not going to take any onus on themselves that it's going to work. They're just going to read the owner's handbook and look at how that system's installed and tell you that, yeah, they did it right, according to the manufacturer. But in years past, they would not even touch those systems. We don't know enough about them. All I could do with an early streamer emission air terminal would be kind of go back to that one diagram and say, yes, you got 2 paths to ground and it appears to be connected, but I really can't tell you if it's going to help your building out or not.
Great. And then last question here from Jason Crowell. Are the inspections just physical, or is there anything done with equipment that tests continuity throughout the system?
That is one thing that we are working on. We can do continuity tests. NFPA and UL do not require or recommend the testing. It becomes very difficult with continuity, especially getting an actual true ground resistance measurement, because you can't disconnect the lightning protection system from every other connection in the building. So it's interconnected. We have bonding connections between the lightning protection and every service entry, the plumbing, the electrical, any gas piping, as well as interferences in the ground. So at the ground rods themselves, there becomes a ground field. And if there's other metallic, buried metallic objects anywhere close to that, they're going to pick up some of that. So it becomes very challenging to try to get a real reading. The continuity test, you can put 2 points of a meter, you can disconnect the penthouse down conductor from the rooftop cross run conductor, and you can put a probe on both sides of that, and you can verify that there's a signal that goes through that loop and verify things are connected. But the majority of the time, we are doing a visual assessment. We're checking fitting the tightness of the components, making sure everything's securely fastened, no loose connections. We're still trying to find a way, because we get the question all the time. We'll have to basically the hidden details of things we can't see after building construction, after the lighting protection is installed. We can't see it, so we have to presume that it's intact and functional. And, you know, how do we actually verify that the down conductor going through the building to the ground is actually there, if we can't access the bottom side of it? some lightning protection installations will put an access well at the ground conductor locations, at the ground rod locations. And that lets us get to that point. So we could physically run a cable from the roof to the ground and check those 2 points and get a good idea that there's continuity, that there is a confirmed pathway. But we've actually had several clients here recently start trying to work through those scenarios. And the simple answer right now is we can check some continuity, but typically as part of a normal inspection, UL and NFPA don't require it. And looking at all the electrical codes out there, there's not a lot of guidance on exactly what type of resistance measurements you should be getting. Even NFPA says it's virtually impossible to isolate the lightning protection system from everything else to get a true reading.
All right, and I think this will probably have to be our last question here, but Wayne asks, say some of the sacrificial pads come loose, can any adhesive be used to reattach them? Which I'm guessing he means, is there a specific adhesive that needs to be used?
The sacrificial pad, that needs to be compatible with the roof material. The hold down clip that holds the conductor can be adhered generally with anything. NFPA and UL don't specify exactly what that has to be. We use Kimble's M1 structural adhesive because it's waterproof. It'll even set up underwater. It lasts a long time. But you just need to make sure that whatever adhesive is used is compatible with the surface that it's mounted to.
Does anyone else have any other questions for Steve? And everyone who registered for today's lunch, I think there was only 18 that registered. You should have received a Grubhub lunch credit. If you did not, please let me know so I can follow up on the status and make sure you do receive that and have something to enjoy at a later time. If you did get your Grubhub for this lunch meeting and it looks so good, you took a picture, send it to me. I'll post it and we'll see what everyone's having for lunch on these fun things. So it's at least another way to stay connected. From what I saw, we had about 28 participants on today's meeting. So I think that's a great turnout. We look forward to doing a lot more of these where we can supply lunch when we are virtual. And again, just until safely we can get back together in person. But yes, you're very welcome for the Grubhub. We're excited to do this. We have our next meeting on the 3rd Wednesday of November. So we'll be sending out some information as we get those details wrapped up. So stay tuned for that. And again, don't forget in January, we have our fun bowling tournament. So plan ahead, stay safe. We don't have a meeting in December, so it's just November. And we'll see if we can continue to do these things.